Hello, and welcome to Answer Everywhere. Today we're looking at the Bitcoin source code. This is a bit of a departure for me. Ordinarily, on this show, I only look at code that I haven't seen before. In this case, I, at one point, was pretty familiar with the Bitcoin code from working on a thing that was built on it for an organization I can't name. And so that's different. I like to treat this as an improvisation exercise. But in this case, I have some familiarity with it. On the other hand, I've never seen the original Bitcoin code. I don't really remember anything about the many years ago when I was working on it. And so while we're not starting with a blank slate, I think we're starting with relatively little information. This is all in C++. And this claims to be the original Satoshi code posted on the internet. I'm not sure how to verify that. And there are a few different places. There are a few different versions of the code that were posted. And I got a few snapshots of people claiming this was the original. And I'm just going to stick with this one. And if there's anything that looks a little bit suspicious, maybe we can jump around to one of the other ones. As I have mentioned, I am building a fund, a open source software fund, which will bring about the flourishing of humanity and a utopia on Earth of open source. And you can donate to that fund. Since we're doing Bitcoin, I put a Bitcoin address in the description. You can send Bitcoin there. You can also send Monero. I put a Monero address in the description if that's more your thing. And so let's check this code out. This is, as I said, C++. I think I said that. Satoshi Nakamoto, nobody really knows who he or she or they are. But my impression from the code back when I worked on it was that the original code was probably a well-versed C++ developer, but not like a super wizard. There was some awkwardness. There were bugs, I believe, in the Bitcoin protocol that later had to be replicated by all Bitcoin clones and forks in order to be on the same net. And so we might see some of those. I'm not expecting the code to be super clean. I think that kind of at the time, this was more of a proof of concept that this sort of technology was possible. And where to start? We have UI. I don't think UI is the place to start. I guess since SHA is so important, we'll look at SHA. This is hopefully, I forget how it's done. This is hopefully just some importing of the of an existing SHA routine rather than one from scratch. Script.h and script.cpp, these may be for Bitcoin scripts. There's a Bitcoin like programming language that consists of opcodes. It's a stack-based language. They describe it as Forth-like. And then we have market and market.cpp. Those are probably useful. Main, possibly useful. Key should be about private and public keys. IRC, I don't know what that would be. I don't think that's the chat protocol. DB is going to be I think the place where Bitcoin transactions are stored. Big num should literally just be a big number implementation. And base 58 should be base 58. Now, base 58, I believe the reasoning was that in base 64, there are letters that look like numbers. And in base 58, it doesn't exist. We don't want 0 and O and I and L characters that look the same in some fonts and can be used to create visually identical looking account numbers. Okay. That's the idea of base 58. I'm not sure if I opened UI, but we should definitely open UI at this point. And then we also have UI base, which is going to be some base class. UI project. I don't know what FPB is. I guess might as well open this up. Nguyen 256. I'm not sure. Something maybe about SHA-256, something about unsigned integers. I don't know. And then who knows what util is. I certainly don't. So we'll try this. Actually, I'm a little bit curious about uint 256. Let's look at that. Hello. Not as many files as I thought. Yeah, there's actually not a lot to the Bitcoin code. I think maybe more than anything, this was a project in getting the correct ideas. Figuring out the double spend problem, which my gloss on it is essentially there's a contested database right, and there's some game theory reasoning about how rights to that data structure work, and you can believe that reasoning or not believe that reasoning, but the basic idea is to have to generalize a data structure to a data structure where there's a competition to do one of the right operations. So in uint 256, we have test uint 256 ad hoc, which is some inline thing, and we have this template int bits thing. We have to keep a separate base class without constructors, so the compiler will let us use it in a union. Okay, but what are the operations here? We have equality. What is this? XOR AND? I guess this is like mainly implementing mathematical operations with a kind of, so that you can do a kind of shorthand for 256-bit thingies, is what I'm going to guess this is. We'll keep it open, but we'll move on back to something that's more like fundamental or entry point. Hello, hello, hello. All right. Here's SHA. I guess we'll just quickly glance at SHA. This should be just some implementation of the SHA algorithm. We're defining some stuff and we're including standard lib. And other than that, it seems like we're implementing it ourselves. ROTL fixed. Okay, so we have this crypt opt fast rotate. This is some sort of fast rotation. Byte swipe, crypt op byte swap might be available. And if it is, we have this bswap 16. And rot R and rot L, I think, are rotate left and rotate right. I don't know what fixed is. Like a fixed point rotation somehow. And we have these annotations like 5 instructions with rotate instructions, 9 without. Okay, so this seems to be focused on optimizing what assembly essentially this is going to be compiled to. And for this SHA-1 class, we have a link to whatever this is. Secure site not available. This is some looks like a spec for SHA-1 linking to the NSA, and here's SHA-256. So this, I think, is just supposed to be the spec. Although, we're linking to whatever waydaddy.com is. Who knows if it's the real spec or a fake spec. The back door. At any rate, we've got this. This seems to be a re-implementation of SHA. So we have this hash word type, which is just a word 32. And this is a function to initialize the state and some transform. You can pass in a digest and some data. And I guess it's called transform, but I'm supposing that it's just taking the data and like adding it to the digest. That's what, SHA-1, and then we have SHA-256. So, no, wait. Yeah, we do. And then we have SHA-224. And this, SHA-224 is calling SHA-256 transform. And I'm not sure if SHA-224 is just doing SHA-256 and then truncating, or what. And then we have 512 and 384. Why? I don't know. Let's look at the implementation of SHA. This file is public domain. SHA routines extracted as a standalone file from crypto++. Okay, good. We're deferring to some other crypto library. Basically, it seems like we're copying the routines maybe rather than importing them. SHA.cpp modified by Wei Day from Steve Reed's public domain SHA1.c. And we have like start Steve Reed's code. So we're just copying and pasting this code into here. This is somebody else's code. And that's probably the right thing to do. Although it would be nice to import it as a library, I would think, rather than kind of copying and pasting. Both to minimize mistakes and also to make it clear what's going on. I'm not going to look at this in detail because it's hard enough to follow the SHA algorithm step by step, and I don't think we're going to really have any hope of following it in code. But we do see some assembly. If GNU-C, then we have this, I guess, assembly volatile thing. Put assembly version in separate function. Otherwise, MSVC, Microsoft Visual Code 2005, SP1 doesn't generate correct code for non-assembly version. All right. So we have some assembly code for the SHA, what is this, SHA-1 or SHA-256 at this point? This is SHA-512, I think. And we may have something similar for SHA-256. I don't know if at this point Satoshi was trying to figure out which SHA version to use or what. I believe they ultimately went with SHA-256, right? And a lot of times people would use ASICs for things like Bitcoin mining to do fast SHA instead of assembly running on the CPU. Here is script.h. So this looks like this is now the opcode stuff. We have a bunch of opcodes. We have an enum. And the enum has sig hash all, sig hash none, sig hash single, and sig hash anyone can pay. I think this is kind of vaguely ringing a bell. Sig hash single. I think we check the signature, and for all, I think we check all the signatures, and anyone can pay. I'm not really sure what happens, but let's look these up. Signature applies to one input and all outputs. Okay, so this is describing what the signature is, I guess, signing. A signature hash flag is used to indicate which part of the transaction is signed by the ECDSA signature. Okay, so Bitcoin is P2P. Yes, that's right. Jose is asking how to implement P2P. Oh, maybe you're asking, Jose, where the P2P-ness of Bitcoin is implemented. And we will get to the P2P-ness. We haven't gotten there yet. But this is kind of part of it. You can think of this as part of it. So we need to specify what is signed. Why do we need to specify this? Because you need to check the signatures, and you need to know which parts of the signatures to check. In theory, you could check all of the different permutations until you find a signature, what is actually covered by the signature algorithm. But that's incredibly inefficient. Remember, the premise of Bitcoin is that every person wants to have like every coffee transaction around the world recorded on their computer. And so this has to be done with some sense of efficiency if you want it to be usable at all. So what does anyone can pay? Anyone can pay. So all or anyone can pay says the signature applies to one input and all outputs. None or anyone can pay. Signature applies to one input and none of the outputs. And single and anyone can pay. Signature applies to one input and the output with the same index number. So we haven't seen a transaction. Maybe it would be good to see the transaction code first. But maybe we won't do that. We'll look quickly at the opcodes. We'll look at the transactions at some point, and then we'll come back maybe to the opcodes. So the opcodes are just an enum, and they have values like 0, and 76. So you have things like push data, like pushing it onto the stack, push data 2, push data 4. I'm wondering if push data 2 and 4 are pushing two things onto the opcodes. Push data 1 takes the next 1 byte. Okay, so we're operating on bytes as the number of bytes to push on the stack. Push data 2 takes the next 2 bytes. Push data 4 takes the next 4 bytes to the something or other. Once data items are on the stack, it is possible to use opcat to join them together, creating larger items for purposes such as file hash verifications and more. Okay, so we can use opcat at some point. Then we have op2, op3, op4, op5, op blah, 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 op16. I don't really know what those are. Let's look up op16 Bitcoin and also op4, just to make sure we're getting relevant pages. What if we just find Bitcoin opcode reference? Op2 to op16, I saw somewhere. The number and the word is pushed onto the stack. Okay, so this is just treating the thing after the underscore as a literal, and we're just pushing it on the stack. Okay. And then we have control opcodes, like no op. Ver, I think, is verify. If is used for conditionals, not if. Verif, somehow different from, I guess verif is probably verify if, ver not if, and so on and so forth. And then return. Although verify is different from ver. So how is that? What's up with that? So op verify marks a transaction as invalid if the top stack value is not true. The top stack value is removed. But what's op ver with no? Op ver is transaction is invalid unless occurring in an unexecuted op if branch. So something about branching and verifying. And it looks like op verify is like verify at the top level or something. Then we have stack ops to alt stack. I don't remember anything about an alt stack. You can drop things that you pull off the stack. You can duplicate. I don't remember op3 dupe versus op2 dupe. Let's try this. Match case and not whole words. Okay. So op dupe duplicates the top stack item. Op2 dupe duplicates the top two. Yeah, okay. And then drop removes the top two. Oh, to drop removes the top two, and drop should just remove the top stack item. So these are all stack operations, and we're just sending them as bits in the Bitcoin transaction. And you have splice ops, like concatenating two things, checking for substring, I believe is what op subster is. Left and right, and size. Left and right, made to do with branching. Keep only characters left of the specified point of a string, disabled, and opt right is disabled. So cat, substring, left and right are all disabled. Fine. And then we have invert and, or, I don't know how invert is different from not, and also numeric, et cetera, et cetera. So this is building up a language. We've seen a bunch of different languages. We've seen even a few stack-based languages, but this is the Bitcoin opcode language. And they have get opname, which is really just a map from the opcode enum to the string that tells you what its name is. And you can see all that is just a case analysis. And then we have this value string where you pass in some stringy thing. We check that its size is at least 4. And if its size is bigger than 4, we convert it to a hex num. And why? And we've got some commented out code. So I guess this is taking the vector of unsigned cars. These are the vector of bytes and converting it to a hex string. When are these opcodes used? Yes, essentially that's right. So DF is asking, and hello, Sreyan, Sreyan. Yes, Bitcoin had what you can think of as smart contracts, in a sense. The main difference is that it's a really constrained form of contract. The contracts are all things like send money to this address, or I think request money from an address. Request that money be sent to an address is also one of them. But it's a deliberately very constrained set of contracts. And then things like Ethereum that followed on, we're trying to generalize what Bitcoin was doing. One possible way you can think about this is we've looked at things like Bazel, which uses Starlark, which is kind of a constrained form of Python. And the idea is that we want to limit the power of the language that we use to describe our build files so that our build logic is something we can reason about. Similarly, we've looked at eBPF, and that has a constrained kind of language you can use to push programs into the Linux kernel. And the idea of constraining the language there is that if we're going to take a program from user space and run it in kernel space, then we want to have some sort of guarantees that they can't do arbitrary code execution and try to take over the computer. So there's a general theme in computer science of having, if you want safety, of really constraining what can be expressed. And Bitcoin, because it was the first thing that figured out how cryptocurrency can work, really had a very constrained language. And then the idea of smart contracts is like, let's somehow make it less constrained, but also still a system with enough structure that people can use it. All right. We have a stack string, which is going to turn some stack into a string, I would guess. We're calling value string on the things that we get off the stack. Then C script, maybe coin script, has this vector of unsigned cars. And what operations do we have? We have push int 64. So we can give it an int 64 and it will push it onto the stack. And we check that if we send in -1 or n is bigger than 1 and less than 16, then we are going to call pushback on, I assume, the stack. I don't know where pushback is defined yet. And we're passing an n plus the first opcode -1. So we're pushing the nth opcode, assuming I thought op1 was 0. So if we pass in 0, then what? This will run, right? If we pass in 1, this clause will be true, and we'll call pushback. I think op1 is 0, -1, that would be -1, +1 would be 0. So we're pushing, I guess, the 0 opcode. I think that's right. We can double check what op1 is, but I don't want to scroll and lose my place. Otherwise, we're going to take whatever this n is, make it a big number, and shift. We're going to call it big number get VCH. Vector, character vector, I guess is what VCH is. Turn the big number into a character vector so that we can put it on the stack. And then we're going to do this shift operation, which I assume just writes this character literally onto the stack, which I think means we've overwritten, we have an override for this shift operator. And then we're going to return a pointer to ourselves, which is like the new stack with more stuff on it. Push uint 64. We now have a uint. We have kind of the same logic as before. And this is almost entirely the same. I think this is literally the same implementation. Okay. And then we have a bunch of public methods. These are protected methods, these push. So I guess pushing onto the stack is protected. And then public methods, we have operations like plus. You can, I guess, add two scripts together. And if we add A to B, then we call insert on the end and the beginning of B and the beginning of end. And I think that probably that just says concatenate the A script with the B script. And then we have, so that's plus equals, and then plus gets the script A and adds the script B and then returns. That's just concatenation. And then we have a bunch of things like here. If we, I guess, create a script with car B, then we're calling operator less than on B. Here's the overriding of the operator. And if the opcode that we pass in is a single byte end, I don't know what end means in this instance, but we're going to insert at the end of our script the opcode, the single opcode, which is what I was hypothesizing was going on. Otherwise, we're going to assert that the opcode is bigger than or equal to the double byte end. Oh, okay. So single byte end is, I guess, the opcodes are bytes, and I think single byte end is just the byte where that's the last of the single byte opcodes. Just like in ASCII, you can test whether something is less than A to see if it's in the alphabet or whatever. And then opcode, this is just checking that we are in a double byte opcode. And we're going to insert at the end the first part of the opcode, and then we're going to insert at the end the second part of the opcode. I'm seeing some misbehaving about internet connection, so hopefully I'm not dropping off. We have this get op, which will take an iterator and an opcode ret, maybe to return, and a vector of like a character vector to return. And what we're going to clear the return vector, check if PC is bigger than the end. And then we're going to find out where the instruction is. I'm not going to read all this code, but I think that we're just finding out what the opcode is. And then we have eval script. We give it a script, a transaction, and the script and the transaction are const, so they're not going to be modified. N in is, I guess, probably the number of inputs of the transaction. Int hash type. I guess, I don't know what the N of hash type is. This is some encoding of what type of hash function to use, I think. And then we have a vector of unsigned cars, and that's the stack. So I think we're modeling the stack as a each line of the stack is a vector of cars, which we have seen. And then the stack, you can push on lines and pull off lines. So that's the outer vector. So it's a vector of cars. You can think of this inner vector of cars as essentially a string, in which case this would be a vector of strings. But this is a vector, this, is not a C string. It's conceptually a string with different operations and so on and so forth. Is mine, presumably you're going to give it a script. You're going to give it a script public key, and it will check if that public key corresponds to a private key that you own. You can extract the public key from a script. You can extract the hash. You can sign signature. Is that different from just signing? So sign signature, you give it a transaction. It says tx from and to tx2. I'm not sure I don't remember what from and to mean. I would have thought from and to would be addresses, but these are transactions. The number, I assume, is number of inputs. The hash type is sig hash all. So we're going to assign all the things, and then we're going to give it the script, presumably the script we want to assign. And then we have verify signature. All right, so that's the header for the script. Here's the implementation. Let's look at eval script. See AutoBN context. We have some PC context. AutoBN, not Autobahn. I don't know. But we see some defines for stack top here. We get it. PC is the beginning of the script. P end is the end of the script. I don't know what C stands for, but that's the, so it's like I think that we're going to use this as a pointer to the script rather than storing the beginning for all time. And then we have begin code hash, which is set to script begin as well. And then we have an execution, which is a vector of bools. And then we have a stack and an alt stack, which are vectors of val types. I guess, I don't know what the value types are, but they exist. And so while the pointer to where we are in the script is not at the end, fexec is going to be set to, we're going to call this count function on passing in vfexec begin and vfexec end and false. What was vfexec? Verify? This is presumably maybe checking if there's any, if any verify step has returned false, I think is possibly what is going on, but I'm not sure. And then we read the instruction. We create a place to hold the opcode and a place to hold the push value. We call script get op on the push value and the pointer to where we are in the script, and the place to hold the opcode as an out parameter. And if we get, so I guess get op returns Boolean about whether it successfully got the operation. And if we, if this returns false, then if get op returns false, then this whole function eval script returns false. We have failed to evaluate the script. But if we successfully got an opcode, then we're down here. If fexec is true, and the opcode is less than or equal to push data 4, then on the stack, we're going to push back the push value. And I guess we got the push value out from get op. So get op not only, so let's say you push on a signature to the stack, which is one of the things you do in a Bitcoin transaction. Then you get back not only the opcode that says push this signature onto the stack, you also get back the signature itself, I think, which is what will be populated with push value. If this condition fails, then we are here. We want to check fexec. I think fexec again is like, have we failed? If it's true, then we have not failed, is how I'm interpreting it. And we check if the opcode is between the if statement and the end if, which I thought they were right next to each other. But these might be the control opcodes in general. And then we do a case analysis. We switch on the opcode. And these are all push values. These are pushing, I think, literal numbers. 1 through 16, maybe op1 negate is -1. And then we push that onto our stack, which is the evaluation stack. Can I explain the switch? Do you mean this switch here? Well, that's where I am. Let me know if you mean some other switch. There's probably a delay because I'm having YouTube is telling me I'm occasionally disconnecting. So there might be a delay with chat. if, and then down here, so these are the opcodes that push literals onto the stack. Now, if we're down here, then these are the opcodes that have control. So if it's a no op, then we break. It's no op, so that's the easiest implementation. Op ver is something about verification. And so what we're going to do is we're going to get the version as a big number. The version should be some probably static constant, essentially. And we're going to what? Op-ver. Maybe op-ver is op version. And we're going to push back the version as a vector of bytes. Let's try, not that. See. Let's try op-ver Bitcoin. Is there an underscore here? Current see if we can find, so we're on line 111. See if we can find version. Oops. Version is the literal 101. It's a static const int. Whoa, no. Sorry. This seems to be literally putting the version on the stack. I don't know what else could be going on, or maybe version is used to initialize the big number. Maybe the big number, but I don't know. So G big num. Generic big num module. So G big num is from OpenSSL. All right, whatever. Oh, C big num is what I want. So what is the BN? I don't know. So it's some big number. I think this is really just the version. Although the let's ask ChatGPT. What does the op-ver opcode do in Bitcoin? Yeah, I think it is just, but the thing that's confusing me is the at least I was reading the Bitcoin script wiki thing as saying that op-ver is something about only being an op-if branch. So ChatGPT says, which is defined under which Bitcoin, however, op-ver is considered disabled or reserved, meaning it cannot blah blah. It causes the script to fail immediately. It says it's a placeholder. I think it's just putting the version on this. The thing, I don't know what it does now, but at least in this code, that's what it's doing. And I guess it really, there is a constraint on it. And the constraint is that to verify op-ver, you have to be in this part of the code. So I think that's not a constraint at all. Never mind. All right, so then we have the real control nodes, if, not if, verif, and ver not if. And we're going to treat these all in the same code block. So we'll set f value to false. And if f exec, then we check whether if the stack size is too small, we return false. Otherwise, we get the thing at the top of the stack. And this check is here so that this is a valid call. And if it's op verif or ver not if, then we set f value to, we take the version and we shift it. We call this shift equals, right shift equals on the vector of the character vector as a big num. So what is this doing? I assume we're using the version so that we get different behavior for different, if we change the version of Bitcoin, it gives us, I think, some flexibility for changing the behavior in the future because it's bound somehow to the version. And otherwise, we cast the character vector to bool. Why? I don't know. And then if the opcode is op not if, or the opcode is op ver not if, we set f value to the opposite of f value. So that's the not part. And then we call stack pop back, popping the thing on the back of the stack. And we push the f value onto the exec stack. And what is confusing me is, I guess by the time we're calling verify, we've already done the work we need to verify. I would have thought we were at some point going to like check a signature. But I think we are, essentially it's like something like verify and then true or false. And verify true is true and verify false is false or something along those lines. It could push a dummy value for debugging purposes. That's possible. It seems to be disabled according to ChatGPT, the op version thing. All right, so I guess verify, if, not if, verif, and ver not if. Where's if handled? Here's verif and ver not if. That's just doing the shifting. This handles op not if and ver not if. And where's op if handled? We don't trigger any of these. So we just, we trigger this else condition. So like if foo, this is just saying like foo is going to either be true or false, and that's just the value we're returning for the if operation. Okay, so op else is basically going to do the opposite, right? So we check if the exec stack thingy is empty. And assuming it's not empty, then we set the back of the exec stack to be the opposite of it. So this is like switching branches. And then we have end if, which is going to be similar. Verify is really what I'm the sort of thing I'm looking for. We check if the stack size is too small. We cast the top thing to a Boolean. And oh no. Yeah. So where do we like check signatures? But anyway, this is all pretty interesting, but I want to get to the crypto. But this is the implementation of the stack language. Okay, check sig verify and check sig. This is the sort of thing I was thinking of as verify. The sig verify one. All right, we checked the stack size is not too small. We set the character vector for the signature to be the, I guess, the second thing back. And we set the public key to be the first thing back. Assuming, I don't know what stack top does, but I'm going to guess that's what -2 and -1 mean. And we might have some debug printing information. And we have a subset of scripts starting at the most recent code separator. So we have this script code with p begin code hash and p end. I don't know where p begin code hash was set. I think we saw it set at the very beginning. It might have been modified since then. And then we drop the signature since there's no way for a signature to sign itself, right? So we have a bunch of bytes. One section of the bytes is the signature itself. The signature can't sign itself, so we delete the signature, take the resulting string of bytes without the signature and hash that and check the public key, and that should be equal to the signature essentially that we dropped. So we look in the script code, we call find and delete, and we call check sig. On the sig, oopsie, no. We call check sig, passing in the sig, the pub key, the script code, tx2 in NIN and N hash type. And then we get success or falser or non-success. We pop off the stack. I'm guessing the signature and public key. And then we push onto the stack either true as a character vector or false as a character vector to indicate whether, according to whether we succeeded or not. And if the opcode is, in addition, if the opcode is check sig verify as opposed to just check sig, then if we are successful, then we pop the thing off the stack. Otherwise, we set PC to the end. And I guess that means that we don't do any more checking, whereas in this case, we can check more. And I guess this looks like early fail behavior. Like you can maybe check a signature and it doesn't fail the script completely in some cases, but verify will fail the script is what I think is going on. We'll check that in just 1 second. I kind of want to see where tx2 is set. Let's see if we can find out. Oh, it's passed into a val script. Okay. So let's find check sig. We have this. Equality is checked to the top, between the top 2 stack items. But is there a... Here we go. This is what I'm looking for. So for check sig, the input is the public key. The output is true or false. The entire transaction's outputs, inputs, and script from the most recently executed op code separator to the end are hashed. The signature is used by op check sig. The signature used by op check sig must be a valid signature for this hash and public key. If it is, 1 is returned, 0 otherwise. Check sig verify, it returns nothing and it can fail. It's the same as check sig, but op verify is executed afterwards. And then where's op verify? It marks the transaction as invalid if the top stack value is not true. The top stack value is removed. Okay. So I don't really, you have to know more, I think, about the language to know what the real differences that are there. I'm sure that the people who use Bitcoin regularly know what those are, but I just don't remember, and it'll take more than a couple of minutes to get a real handle on that. So I'm going to just move along for now. Here is market. I have no idea really what this is going to be. We have some flow through rate. We have an advert insert, advert erase for a product. Is this for adding advertising to Bitcoin? Add atoms and propagate. So add atoms and propagate take some v atoms and some origin. We have a user with atoms in, atoms out. You can get hash, get atom count. We have a review. This looks like products and reviews. What on earth? So let's look this up. Bitcoin product. No. Let's just take this whole thing and give it to Gemini. What does this code do? I'm wondering if this is a feature that's not in the regular Bitcoin. The provided code snippet appears to be related to a product advertisement system, possibly a digital marketplace. Yeah, here's a breakdown. We have reviews for a product. We have users. We have the product. You can insert an advertisement. This is wild. Is this real? I'm not positive this is real. So this is a place now where we can check the other versions claiming to be the original Satoshi code. I'm going to guess that this is real. So we're looking at Bitcoin v0.1. We can also look at this thing. And what are we in market? Yeah. That's pretty wild. How about Satoshi Bitcoin product advertisement? I had a feeling this was going to be impossible to search for. Let's try ChatGPT in a new window. So did the original Bitcoin contain code for product advertisements, e.g. creating an ad marketplace? All right, let's ask Gemini the same thing. Did the original Bitcoin code have functionality for a product/advertisement marketplace? No. Focus on atoms. The code snippet uses the concept of atoms as a unit within the system. Bitcoin itself doesn't have such a concept. Let's try Bitcoin market.h. Satoshi source code. Yeah, I don't know. This is hard to search for. Hopefully someone out there is a Bitcoin expert or a Bitcoin historian, and you can tell us what is going on at this marketplace. Maybe there's a comment in the CC file, the CPP file. Critical block, CS map products. Need the stack that this equivalent or delete comment, blah, blah, blah. I mean, I don't know. What if we just search for this comment? Yeah, I don't know. Let's move on though. So here's the main. We have an out point and in point, a disk transaction position. I'm guessing this is the transaction that's stored on disk, a Coinbase, in and out, transaction inputs and outputs, the transaction itself, the block index, the wallet transaction, and a key item. I forget what the Coinbase is. So a transaction it's a ledger. It's a distributed ledger at its heart. So the transaction has some input. These are like where you're going to source the money from. It has some outputs. Those are where the money is going to. And peer-to-peer wise, somebody, I think Jose was asking about, yeah, it is a secret Bitcoin feature. I think Jose was asking about P2P. before Bitcoin, there were a bunch of peer-to-peer databases or like peer-to-peer hash tables. And so you can think of like your regular bank account as being a model of a transaction ledger. You tell it where which account money is coming from, which account money is going to, and if the account money is coming from is your account, and the account money is going to is like the Amazon account, then that's you spending money at Amazon. On the other hand, if the account, if your account is on the other side of the ledger, that's somebody sending you money, and so on and so forth. And so you can take that idea of a ledger. It's a kind of database, like an append-only database. You don't typically go back and erase transactions that already occurred. Instead, if you want to like revert money, you add a new transaction going the other way, and so on. And so you have this database, and you can relatively easily spread it out using traditional peer-to-peer mechanisms, like something like Kademlia, where you just store bits of the hash. You store bits of the transaction ledger in different places. The problem is that for something like currency spending money, there's an incentive to fake the transaction ledger, to have people have it look like people are giving you a bunch of money. And so you have to worry about not only distributing the ledger among different people, but making sure that everyone has the same vision of the ledger. So that latter problem is really the hard part. But for understanding most of the code, we can focus mainly on the easy part, which is that we have some transaction. Transaction has inputs where money is being sourced from, and has outputs where money is going to. And then we're going to bundle those transactions up into blocks. So rather than storing line by line on different nodes of the distributed database, we're going to store a block of transactions together. And then a wallet, I think, is conceptually really just a private key and its associated public keys. That's where money is sent to, because the way that the opcode system works is in order to spend money from an address, you have to prove that you have that. So the address is really just a public key. And in order to spend the money, you have to sign the transaction. And to sign the transaction, that's a proof that you have the private key. And so the private key is really the wallet is a collection of private keys. And then a key item, I don't know what that is. I'm guessing either the public or private part of a key, or maybe the public-private pair together. We have some constants, like max size is whatever this is, 0.2 something million or billion. We have a coin, which is some large amount. We have a cent, which is 100th of a coin. And we have Coinbase maturity, which is 100. And we have BN, proof of work limit, is this thing. We're going to negate 0 and shift it over by 32. All right. And then we're keeping track of some sort of critical section. We saw the critical section also in the market advertising feature, but that's no longer a thing that exists, apparently. And a bunch of other stuff. The Genesis block, I think, is going to be the first block of the database, and so on. And in fact, I think to understand main, we will need to talk about Merkle trees and so forth. But maybe we'll do a quick spin through main, ignoring the crypto, and then we'll get on to some of these other files that I think have the crypto in them. But we see things like add to wallet, relay wallet transactions. You can load a block index. we have this Bitcoin miner, which is a Boolean. I guess maybe do you have a Bitcoin miner or not? You can get the balance. You can create a transaction, giving it a public key, a value, a new transaction, which is a C wallet transaction, and a fee. I think this is just the fee for essentially paying miners. And then you can commit transaction spent, which I guess commits the transaction. And you can send money, giving it a public key, a value, and a new transaction. So this is CDisk transaction position. And we have, it's got a file, a block position, and a transaction position. So this is going to look in some file, I guess, find a block, and then within that block is going to have a transaction. We have an endpoint, given a transaction, somehow, I don't know, figure out what is, where the end parts are, I would guess. And we'll just, this is main, we'll just scroll through main a little bit. Here's this C transaction class. The basic transaction that is broadcasted on the network and contained in blocks. A transaction can contain multiple inputs and outputs. So this is the model of the transaction itself. I would have thought this might be in its own file, but it's not. We have a version. We have just a vector of ins and a vector of outs and a lock time. I don't know what the lock time is doing, but when we initialize, we call set null. And then we have this implement serialize thing, which is going to read write version, set version of this version, read write in, read write out, and read write lock time. This is just, I think, serializing in, out, and lock time, and version, etc. Set null is just going to clear in, out, set the version to 1, and lock time to 0. Is null is going to return whether the in and out are empty. I guess ignoring version and lock time. Get hash is just going to serialize. It's going to call serialize hash on this. So this is going to somehow take this. I think this is just a pointer to the struct, right? And we're going to, I guess, treat that as an array of memory and hash it. I think is what's going on there. Is final is going to, so I think is final is going to check that we haven't really talked about, but I think Bitcoin users know that it takes some number of blocks for a transaction to be confirmed. And the basic idea there is that the proof of work is such that undoing it is nearly impossible. And so once it's nearly impossible, you treat that transaction as final. So I think that this is some logic to handle that. So if lock time is 0, or lock time is less than best height, then we return true, it is final. Otherwise, for every transaction, for every input, we check that for every tx in, what is tx in this case? And what are we iterating over? We checked that I can hear my baby upstairs. I didn't know she was home. That's why I was laughing. So if we check that all the transactions are final, and if they are, we check if any. We check if any is not final. If any is not final, we return false. All of the tx ins must be final in order for the whole thing to be final. And if all of these checks pass, then we return true. I'm a little bit confused about what ctx in is, since we are implementing a transaction, and even really where we got it. But I don't know. We'll see it somewhere. And then we have is newer than some transaction. And I forget what pre-val is, but I remember working with it a lot in the old days. And what? This is going to do some iteration over the inputs. and check some sequences. This is just, I think, essentially checking what block it was created on and this comparing blocks. Is Coinbase, let me look up what a Coinbase transaction is. A Coinbase transaction is the first transaction of a block. It's placed there by the miner when they construct their candidate block so they can claim the block reward. Okay, so then in Bitcoin mining, the miners are paid by block rewards, and that the Coinbase transaction is the first transaction in the block, and that's where they claim the rewards essentially. Is I think what that's saying. And then we have check transaction, which is going to do some sort of consistency or sanity checking. We check that it's non-empty. We look at all the outputs, and if the value, if we're trying to send negative money, which would essentially send money the opposite direction, it would send money to you instead of you sending someone money, that's an error. If it's a Coinbase transaction, we check something about the signatures. The script signature size can't be less than 2 and it can't be bigger than 100. Otherwise, we look at all the inputs. I don't really know what a VN is. And if the TXN previous out, I think TXN previous out is the input to a transaction is I was describing it, the ledger, as it's kind of like your account. But if I remember correctly, the way it works is you need to show that you have, if you're sending someone $100, you need to show that you have $100 to send. And the way they do that is that the input transaction refers to previous output transactions where somebody sent you $100. Maybe a bunch of people sent you $2, or maybe you funded your account from some bank account that held US dollars in cash or whatever. But at some point there needs to be inputs that the TXN thing needs to contain pointers back in time where it received funds, or else you can't send money. I think that's what previous out is, but let's verify that. TXN elements. I'll just preview out Bitcoin. What does prevout and end mean? Transaction consists of a number of inputs and outputs. Outputs define a script that need to be executed to be able to spin blah, blah, blah. The prev-out field is the transaction hash, and the n is the index of the output. A transaction input must be able to reference the output it is willing to spend. Outputs in a transaction are ordered. An output can be referred to by specifying the transaction ID of the transaction it has been defined in. Chris is saying my work is amazing. Keep up. Next time. All right. Thanks, man. I appreciate it. All right. So I think that's what a typical Bitcoin transaction is. Blah, blah, blah. Unspent coins from previous outputs are referenced by the inputs. Yeah. So I think that's what it's saying. So that's what previous out is. Is mine. So is mine is going to iterate over the output transactions and call is mine on each of the TX outs. Okay, and so now I think I understand more what we're iterating over. We are in a transaction, and I guess like the thing we're iterating over are essentially the coins, maybe, or the sub transactions that our transaction is built up of. We have other things like get debit, get credit, and then we're just iterating over each of these things. And so, and read from disk. I'm going to kind of skip over them. Now that we have a sense of what a transaction is. A Merkle transaction is a transaction with a Merkle branch linking it to the blockchain. So now we're talking about blockchains. I guess we might as well do it. We have a wallet. Okay. So blockchains. A transaction with a Merkle branch. Okay. I'm going to assume that like most people. So most people who are watching this because they're following my other work probably don't know much about Bitcoin. Most people, a lot of people who come here, maybe if you're coming here from the Bitcoin space, Bitcoin may be second nature to you. So I think that the audience like bifurcates into two groups, one of whom this will be completely trivial, and one of whom I'm not going to be able to do it enough justice for people to really understand what I'm saying. But a Merkle tree is essentially you have a notion of a hash. I'm going to assume you have some sense of what a hash is, like a SHA hash or an MD5 sum or something like that. And you build it up in a tree structure. It doesn't have to be a tree. You could think of it as a chain. But the idea is it's maybe a little bit like a linked list. If I hash the parents that came before me, then that's a kind of time stamping operation. Because I've proven that I had access to the thing that came before by putting its hash in the thing that I wrote down. So that's kind of part one. There's a sort of time stamping aspect to it. And part two is it's hard to invert a hash. So in order to kind of like falsify the timestamp or to alter a database built up of hashes in any way, you have to invert the hash function, which is hard to do. And by hard to do, I mean impossible in any practical sense. Like if a nation state wanted to invert a single transaction, they could possibly do it, maybe on the order of years. To do it at scale on multiple transactions would be like the universe would have collapsed, I think. So here's a depiction of what the Merkle tree looks like. Well, let's read the definition first. In cryptography and computer science, a hash tree or a Merkle tree is a tree in which every leaf node is labeled with the cryptographic hash of a data block, and every node that is not a leaf, called a branch, internode, or inode, is labeled with the cryptographic hash of the labels of its child nodes. A hash tree allows efficient and secure verification of the contents of a large data structure. A hash tree is a generalization of a hash list and a hash chain. Demonstrating that a leaf node is part of a given binary hash tree requires computing a number of hashes proportional to the logarithm of the number of leaf nodes in the tree. Conversely, in a hash list, the number is proportional to the number of leaf nodes itself. The Merkle tree is therefore an efficient example of a cryptographic commitment scheme, in which the root of the tree is seen as a commitment, and the leaf nodes may be revealed and proven to be part of the original commitment. So commitment schemes are interesting enough that we should... So this is talking about partial reveal, but... A commitment scheme is a cryptographic primitive that allows one to commit to a chosen value or a chosen statement while keeping it hidden to others. So you can imagine this is crypto, so there's lots of crypto examples, but you can imagine as a kind of silly or toy example, like a magician might use a commitment scheme to commit to, like, he thinks that your card is the ace of spades or whatever. And then he's going to do his magic trick. And at the end, he's going to reveal that he thought it was the ace of spades. And normally in a magic trick, that's done by like having the assistant write it down on a marker board, and they like turn it around at the end. And it's kind of the same sort of thing. With the ability to reveal the committed value later. Commitment schemes are designed so that a party cannot change the value or a statement after they have committed to it. That is, commitment schemes are binding. Okay, so that's it. So it's a way of committing as well. So here's a diagram. And so the leaves, I guess, are the data blocks. So we're going to hash L1. That's going to give us this inner node. We're going to hash L2. That's going to give us this inner node, and so on and so forth. Then we have transformed for each data block. We now have a hash block. It's a hash of a single data item. And then we just concatenate these two blocks together and produce a new hash. And similarly for these. And now we have two hash blocks that are, this hash block contains the hash of L1 and L2. This contains the hash blocks of L3 and L4. And then finally, we combine them together to make a single hash. And if I remember what Bitcoin is doing, that essentially these are all the transactions, and then the everything hashes down, everything in the block hashes down to a single hash. And see if we can find a transaction block, Merkle tree. See if we can figure out what exactly is contained in the block. There's something like this. We'll open a few of these. I don't know if any of these are erroneous in any way. This one has colors. Oh, no. I want just the image. Can I not do that? Well, here's one image. So we have transaction 0, these are all transactions. I don't think the 0 indicates anything, but these are transactions. We hash each transaction to get these here. Then we combine these two transactions to make a combined hash to get the yellow stage. And then we hash all of these to get the root hash. And that's in the block header. So the block header contains the hash of all the transactions together. The block itself contains the transactions. And if we believe this diagram literally, the block itself also contains the intermediate hashes. I don't know if that's true, but maybe it's true. And then the block header also has the previous hash, the block that came before, and a nonce. A nonce is a number used once, I guess is the shortest way to say it. It's a number that you create and is used in the hash. I think you like prepend it to somewhere. And the idea there is that's part of the proof of work thing. So you, if I recall correctly, the way it works is you do get some root hash here, and then you like prepend or append to the root hash, like a number that you generate, and you try to construct the number so that the hashed value has a certain structure. So it has like some number of zeros in front of it. Like let's say you want to produce a hash where the first 4 bytes are 0. You kind of, I think you fool around with the nonce until you find one that has that effect. And that's essentially what mining is. But let's compare that to some other diagrams. So here we have the transactions. They build up into hashes of 2 transactions. Then they build up into hashes of 2 transactions, and so on and so forth. And you keep track of the previous and that. And then what about this one? So we have the Merkle tree. So I think we get the whole Merkle tree, including the transactions, which are the leaf nodes. You have the version, the previous block hash, the difficulty, which is essentially like the number of zeros. And you can see here the block hash has 1, 2, 3, 4, 5, 6 zeros. And the nonce. Let's verify that the nonce is doing what I think it's doing. If we just try Bitcoin nonce. The nonce in Bitcoin is a 32-bit, 4-byte field whose value is adjusted by miners so that the hash of the block will be less than or equal to the current target of the network. The rest of the fields may not be changed as they have a defined meaning. So we should be able to find a block explorer like this one. And can we see? I hope this is Bitcoin and not some other cooler cryptocurrency. It's certainly slow. These are transactions. this should be a block. It does say Bitcoin here. So while that's loading, we'll move along. Okay, so this is a Merkle transaction, which is a transaction with a Merkle branch linking it to the blockchain. I don't know what it means by a Merkle branch, but we'll see what's in it. We have a hash block, a Merkle branch, whether Merkle has been verified. We can initialize the Merkle transaction, and when we initialize it, the hash block is set to 0. The index is -1. It's not verified. We have this get credit thing. It says we must wait until Coinbase is safely deep enough in the chain before valuing it. Okay. I guess this is maybe asking like how much money we were sent if we were sent money. And then we're going to serialize a bunch of stuff. We serialize the transaction, the type, the version, whatever ser action is, like serialize action. This is the version, and we serialize the hash block, the Merkle branch, and the index, and so on. And then we have things like wallet transactions, CT index, etc. Here's a block. Let's see if we're done with our. Yeah, okay, so here's the Bitcoin Explorer block. A total of, what is this? Hundreds, thousands, millions, billions? No, hundreds, thousands, hundred thousands. Yeah, billions. Okay. So here's the hash, and we can see that it's displayed as 00000. That's 5 zeros. But if we actually copy it, I'm not willing to count all of these zeros, but we'll see that that 00000 or whatever is just the display, and that in reality there are many more zeros. So we go over here. It's what, 18 zeros, and an older transaction would have 17 or 16 zeros. So we have to keep changing the nonce until we get all of these 18 zeros, and that's the hard part. And difficulty works by increasing or decreasing the number of zeros that are needed. So if you only need 2 zeros, it's much easier to find a nonce that will produce a hash with 2 zeros than it is to find a nonce that produces one with 18 zeros. So somewhere we should see a difficulty. Difficulty is this. I don't know how to interpret this. I thought it would be like a straightforward conversion to the number of zeros we need, but it's not. It's 79.5 T, I guess trillion. And here's like some diagram of the difficulty over time. And I don't know how to read these charts, but that's what's going on. So let's go back to the code. Here's a block. A block has a version, previous block. It's got the hash of the Merkle root. Keeping track of the time, the number of the bits and the nonce. I still don't know what the end prefix is. Maybe unsigned. And then we have a mutable Merkle tree, and the Merkle tree is modeled as a vector of uint 256s. And we saw uint 256 before, so this is some version of uint that's been modified, I guess, so that it's at max 256. Is that right? I'm not sure. Something about it being something about working as a hash and being hashy as a data structure. Okay, and then we are going to serialize a bunch of stuff, and this is just the code that kind of corresponds to the diagrams that we saw. So let's leave main. Should we leave main? There might be some other interesting stuff here. We have block index. It's like looking on the disk. This is block locator. Describes a place in the blockchain to another node, such that if the other node doesn't have the same branch, it can find the recent common trunk. Okay. And then we have things like map transactions, map wallet. I guess map transactions is a map from maybe hashes to the transaction that is. I assume that when you get a transaction and read it into memory, we're going to hash it and store it so that given the hash, we can look up the transaction. And similarly for wallets and all that stuff. All right, so let's move on from main. I'm not going to look at main.cpp. Here's key. We have private key size, public key size. Key must really just be keys. So a C key is an elliptic curve key. They call it P key, but both public and private begin with P, so that's not the greatest name in the world. We have this SECP 256K1. That's the elliptic curve. I think Bitcoin chose kind of an odd curve, if I remember correctly. They didn't want to choose the NIST curves. Let's see if this is true. Unlike the popular NIST curves, SECP's 256K1 constants were selected in a predictable way, which significantly reduces the possibility that the curve's creator inserted any sort of backdoor into the curve. My personal theory, and I don't know if this is believed by other people or not, is that Bitcoin was created for something like money laundering. And so that the reason for avoiding the NIST keys was to avoid the possibility that the US government has some sort of backdoor that can be used to track people. Is that true? I have no idea. But that's just my current interpretation of events. All right, so this is just key stuff. We can, I guess, duplicate a key by passing one in. We can make a new key by calling generate key. We can set private key. So what does that do? That it's like this VCH. That's like the character vector private key. We set the beginning to the beginning of the vector. Then we call this D2I EC private key. And if that fails, we return false. Otherwise, we return true. So this must somehow write it somewhere. Otherwise, this would be a throwaway operation. And we're only taking one argument. So there's no out parameters. We can get the private key. So whatever I2D is doing, I don't know really what that's up to. But I'm going to just kind of move along. This is already pretty long, right? But at any rate, we can sign and verify. Let's look at sign. So given the private key, we need the private key to sign. We don't need the private key to verify. We need the other person's public key. But given in order to sign, we need our private key. We need the hash that we're going to sign. So we're not given the message for this implementation of sign. We're just given the hash, I guess. And we're returning bool. So I'm going to guess that this VHSig is the out parameter for the signature. So we're going to create this key, call set private key, which I think we saw the implementation of above. And if that fails, we'll return false. Otherwise, we're going to call just key.sign. So we're delegating to some implementation. And for verify, how are these different? So this is verify that takes a hash and a signature. I guess that's for maybe verifying a method, a message for which we already have the public key. And this is verify maybe for somebody else's public key. Okay. This I'm kind of curious to look at the implementation of. Let's see if we have key.cpp. No. But maybe we import something. So we have p key. Where does this I2P stuff come from? Oh, I do T. I2D, I mean. I don't know. Comes from somewhere. See if we can find an Emacs. But if we just look on the internet, I2D, what is it, private key, _EC private key. Oh, I guess this is OpenSSL. So I think we're just using OpenSSL's implementations. I didn't realize OpenSSL had that the Bitcoin the Bitcoin elliptic curve at the time the original Bitcoin was written. Okay, so IRC has receive line from a socket, read IRC seed, and restart IRC seed. Maybe they're using IRC for peer-to-peer messaging. This does seem to be IRC, the like distributed chat protocol. Is IRC distributed? It's not, right? It has servers. But they seem to be using IRC for something. It's a protocol that uses TCP and optionally TLS. An IRC server can connect to other IRC servers to expand the IRC network. Much like conventional P2P file sharing, users can create file servers that allow them to share files with each other by using customized IRC bots and scripts. Is IRC peer-to-peer? So I think IRC is not peer-to-peer. This direct client-to-client, I think, is maybe the thing. So direct client connection is an IRC-related subprotocol enabling peers to interconnect using an IRC server for handshaking in order to exchange files or perform non-relayed chats. Okay, so maybe this is just, since this is like the original Bitcoin code, maybe they're using IRC for setting up an initial peer-to-peer messaging system. I'm not sure, but here's irc.pp. We have this encode address. We have an IRC address which has an IP and a port. And we can put it into one of the Bitcoin's favorite data structures, the VCH. And that's just going to be like a VCH version of the IRC address. We can similarly decode the address. We can send, given a socket, PSZ send. Not sure, but we look at maybe this is the string we're supposed to send. So the string is Pong. And is not equal. I'm not sure what this is doing. Stir of PSZ send, comma Pong is not equal to PSZ send. Then we print that we're sending the PSZ send thing. I at first thought this was a substring, but I'm not sure what stir is. String finds the first occurrence of the null term. Okay, so this is finding the first occurrence of Pong, and it's checking that it's not at the beginning, I guess. I guess we don't send Pongs, or we don't log Pongs. And so we just send it, I assume. And we send it on some socket, and we check the return value. And I guess the return value is the amount of stuff we sent. If it's less than 0, then we didn't send anything. Otherwise, we increment by the amount that we sent and go back up here. And if we haven't finished sending PSZ, then we send the more stuff until we fail, or we have sent the whole thing. And then we have receive line. This is send. This is receive line. I'm going to guess that this receives the whole line. Maybe it waits until we see a line termination character. Like, for example, here we have a new line, and I think R is what, carriage return? Yeah. Okay. So this is just, we're going to call receive until we get a new line. And they have receive line R receive line IRC. So this is receive line on socket. Receive line IRC is going to call receive line that it takes in a socket, but it will like look for IRC things like ping and shut down, I guess. And then receive until takes in a socket. This I don't know what PSZ stands for, but that was the thing we were sending before. And I guess you give it some stuff and it like will keep receiving until it finds some stuff that it's looking for. And then we have thread IRC seed, etc. We have a main function, which is like a test. And it really seems like we are using IRC for messaging. So Bitcoin, Satoshi, IRC. Yeah. Bitcoin client no longer uses IRC bootstrapping by default. And as of version 0.8.2, support for IRC bootstrapping has been removed completely. This documentation below is accurate for most prior versions. Hello, Pavan. Okay, so we are using IRC. So Jose, who may not be with us any longer because it's been like an hour since he was asking about PTP. So now we've seen two aspects of PTP, I would say. One is we've kind of sketched out how the distributed database will work. We haven't really looked at distributing any chunks of the database, but I'll say more about it in a second. And the other aspect is how do two nodes know how to communicate with each other? And at least in the initial version of the code, it seems to be using IRC, probably using the direct client connector, whatever that thing is called, to essentially get a list of peers who are, I'm supposing, in the same channel and want to talk to each other, and then kind of getting IP addresses and sockets from there, and then sending messages to the nodes. With respect to the distributed nature of the database, I had mentioned that there are these distributed databases that are things like Kademlia or Cord, I think is one of the academic papers on the topic. I believe we're not actually doing any real work there. In a lot of cases, the distributed databases, one of the problems that you're trying to solve is like you're trying to share some song, like a sweet Metallica tune, and you may decide to send, let's say you're sharing a Metallica album, and you send one song. You might send one song to one person, another song to another person, and so on and so forth. Or you might break the song up into chunks and send one chunk over here, send one chunk over here. You might want to make sure that there are 3 copies of each chunk. So if one of the nodes goes down, you can still pull it off the network. For Bitcoin, I don't really think we're doing any of that because the premise of running a full Bitcoin node is that everyone has the full database and verifies for themselves the full Merkle chain. And so in that sense, the peer-to-peer aspect is pretty simple. You just share all of the transactions and blocks that you see with everyone else. I'm not sure that that's the way it's implemented, but I think conceptually there's less difficult work to do in that sense. Here is db.h. This is going to start to be database stuff. This, I think, is implementation dependent. I think that there are, back in the day when I was working on it, I think that there were Bitcoin nodes that used level DB, or maybe some precursor to level DB or some successor to level DB to store transactions. This can really be done any way you want. I think there might also be ones that use something like some SQL or like SQLite. I don't know what they use here. I think in a sense it doesn't really matter, but maybe we can find out what the original one used. We have dbenv and dbflush, which should, I guess, flush to db. We have cdb. They might just use their own, they might just make their own system. Erase. We have SS key. I don't know what SS key is. Maybe that's a clue. SS key. This task creates a DGX file for a particular observation. That file contains the support schedule information for the PMDB, which is required to run data validation and generic conversion. CDBS. Is that the database? Consolidated Database System was used for radio and television broadcast applications from 1999 to 2023. Huh. Let's see if that's the same thing that Bitcoin is using. OWL? Is it called? Is OWL the name of the database? DBMS. There's a semantic web OWL. Is it using RDF storage? How about Satoshi Bitcoin original database? So SS key may be something about OpenSSL, which is my first thought, but I'm not really sure what's going on. We have DBT. Are we importing anything? DBCXX as a system file. Berkeley DB? I think it's Berkeley DB. Hey, Berkeley DB. How do you spell Berkeley? The non-music school. So Berkeley DB. If that's right. The SS key is maybe not part of Berkeley DB, but I think that we're probably using Berkeley DB. Let's see if we can verify that. So we have some data stream. Whatever SS key is, we're going to reserve 1,000 of something. We have a DBT data key. I think Berkeley DB is a key value store. And there's going to be some sort of mapping, I guess, from the... No. There's a key, I guess, the size of the SS key, whatchamacallit. And we have this, that's the key. And then we have this is the read operation. You're going to create a place, I guess, for it to live. We're going to set the flags. Something about DB, DPT, malloc. Whatever PDB is that passed in? I'm not sure. I don't see it. I don't see PDB set anywhere. But we're going to call it get on the, we're going to get some transaction identifier. I think probably write it to the dat key, or maybe pass in the dat key and write the thing that we get back to the value, and we get some return back. Or something along those lines. So let's look up DBT. Let's try one more thing. We just search for Bitcoin Berkeley DB and hope that I spelled it correctly. Why is the Bitcoin Core wallet moving from Berkeley DB to SQLite for its database backend? Okay, so Bitcoin Core is the like the publicly released thing, I think, that was built off of this like original Satoshi code. So I'm going to take that to mean that this is really Berkeley DB. That's consistent with what we found when we looked up the header. So I'm going to think that this is Berkeley DB, and that's essentially a key value store, right? that's stored on disk in an efficient way, an embedded database for key value data, historically significant in open source software. Okay. So we're just storing it in some Berkeley DB thing, a key value store. Nowadays, you might use something like Redis if you wanted to be cool, or you might store it in SQLite if you wanted it to just be local. But it does, the database, I think, in an important sense, doesn't matter. Here's UI.h. I don't know if there's a GUI or if this is just some like command line thing. We have event handlers like, oh, I mean, there's on mouse events. We have on close, on mouse events, on idle, on paint. This does seem to be some Windows stuff. Windows in the sense of windowing UI, not in the sense of Microsoft Windows. We have some dialogues like on button, okay, etc. So this has some UI. I'm not going to go into the UI, although I'm curious to see its. Here's an RC. This is like describing things like the icons and the bitmaps. That's like, it looks like static content. Here's UI base. We have WX. Is that the same as WX widgets? Maybe. I'm going to guess it's WX widgets, a widget toolkit, and tools library for creating graphical user interfaces. And I think this is a pretty janky toolkit. Let's see if we can find Bitcoin Core UI Satoshi. Screenshot. Maybe this might be something like what the original UI looked like. The UI may still look like this. I have no idea what Bitcoin Core looks like. Before I forget, let's make a photo of Scrooge McDuck swimming in a pool filled with Bitcoins. All right. So I think this is some WX widget user interface. C++ code generated with WX form builder. I wonder what WX form builder is. This may be a thing to quickly generate UIs based on declarative code. WX form builder. A GUI builder for the WX widgets framework. Codes generation is blah, blah, blah. Okay, so this is a GUI builder for WX widgets, and that's what they used, I guess, to generate the first Bitcoin UI. This is also generated code. We'll ignore it. UI project at FBP. This is some XML that I guess describes what the UI is going to look like. So this is some event mapping between the string on mouse events to on mouse events unstringified that might refer to the function named on mouse events. And it's also going to define properties like the first ID is 1000 and so on. The window style is tab traversal. So I guess when you press the tab key, it's going to traverse on the focus will transfer to different parts of the UI. And this may be the input to the WX widget generator thing. Let's see if you can find this file format, FBP. Well, we get back to this thing. Do we get an example? But we do have this FBP file here. So something is connected. FBP file format. Is the central WX form builder development file that contains project settings and references to the other files used by the project. Form builder project is, I'm going to guess what that stands for. Here's uint 256.h. We already saw that, although we didn't really understand it. I'm just going to move on. Here's util.h. And this is just some stuff like for each. We saw for each used a bunch of times. We saw a loop, which is just for : : So a for loop with, I don't know what the official names for these parts of the for loop are, but essentially they're kind of like initialization, guard, and what happens at the end of each loop. And these are just like essentially mostly macros for, okay, here's like critical section, etc. So these are really just utilities, like a library that, if I had to guess, I would guess that a lot of this stuff came from whoever Satoshi Nakamoto is. Nakamoto? What is it? What's the last name? Let's get this right. Nakamoto. Whoever Satoshi Nakamoto is, I'm going to guess, based on nothing at all, but this is not a huge amount of code, Bitcoin. So I think that I would guess that a lot of these like macros and utilities are utilities from other projects that Satoshi worked on. Maybe they're copied from public projects. Maybe these are utilities that the entity Satoshi Nakamoto created for themselves. But if you know a lot about programming, you might be able to figure out what industry Satoshi worked for by kind of having an understanding of like where, why they liked these particular utilities. These seem like things that you know, things like for each and loop. These are, you can't, it's not like you can't live without them. These are like nice to haves that are like convenience features. And these CPP file is just the implementation of the utilities. And we're not going to close that because I want to make sure that we have hit all of the Bitcoin parts. We are at the end of the code that I laid out, right? Yeah. And I want to make sure that we haven't missed anything super Bitcoiny. And so let's just take a look at the source code again. RC we haven't looked at. DB headers IRC, we looked at all those. License, I don't care about. There might be some more stuff in main. Market was a feature that doesn't exist anymore. Net is networking. We could look at script again, but I'm not going to. Let's find out what's in RC. Let's scroll through main again. Maybe main.cpp instead of the header. And then I think we'll have done our due diligence. RC is some BMP files. These are images, right? Address book. So this is like the static content for the Bitcoin, the WX widgets UI. I don't think I need the main header. Here's the net header. I don't think we looked at this at all, but this is for sending the messages. We have a message header, address, whatever, invis, and a request tracker. Some default port, which is 8333. I don't know what HT-ONS is. We have things like connect socket, get my external IP, so that I suppose I can send it to other people. Get address, find node, connect node. And this message header class. We have this read write macro that we've seen before, implement serialize, which we've seen before. And we're going to send the message, start the command, etc. And so PHC IPv4. This is something about IPv4. I don't know, maybe mapping it from the ordinary format to some format they like better. An address has reserved IP port, etc. get adjusted time. So this seems just like ordinary stuff. Get key is what? I'm just curious whether it's the crypto key or something else. And I'm not sure. We have SS begin, SS end. The SS is the data stream. Flat data P. Yeah, I don't know. I don't think that's the crypto key. All right, so this is just, networking stuff. It's worth seeing this because it is a peer-to-peer app. So we have error PPSZ. So this is the type of thing we're sending. It looks like, and it could be an error. Something went wrong, a transaction. We could send all the transactions to each other so that the miners can create a block out of it. We might send a block itself, a finished block, a review, or a product, because there's a secret advertising system in Bitcoin that I had no idea about, or a table. What kind of table? I don't know. Maybe a table of products and reviews. Maybe like a picture of a nice table that you might buy at the furniture store. Some kind of table. See, inv, whatever that is, it's got a type and a hash. A type in and a hash in. And I don't know what it is. And a request tracker. I'm not sure what request tracker is doing. And then we have references to things like clients, local services, address, localhost, etc. So I think I opened up the CBP version. The main thing I want to know is whether we are still using IRC in here. And yeah, so I'm going to guess that in here, we're going to talk to some server and get like a direct connect. Thread IRC seed, begin thread. There's some threading stuff in here and whatnot, but I don't think we need to. Here's start node. I guess this is the thing that runs when you start a Bitcoin node. So the socket startup WSA data. I don't know what that is. We call it WSA startup. We log some stuff. TCP. So if this is some error that might occur. TCP/IP socket library failed to start, etc. We can get the host name. We're trying to get our host name. And if we can't, then we have some error and so on and so forth. And then I saw somewhere we were like start listening to incoming connections. Okay. So this is stuff that I'm glad we at least saw. If we had seen it earlier, I'd probably spend more time on it, but we are pretty long now. And then finally, here's main.cpp. Let's just maybe scroll through these symbols and see if there's anything super cool, like at the bottom. We have send money, critical block. Oh, no. Send money, commit transactions spent, create transactions, select coins. Bitcoin miner is a function. Let's look at Bitcoin miner. Bitcoin miner started. So we're going to set thread priority on the current thread to the lowest priority, because I guess we are the non-mining thread. Or maybe we are setting the miner thread to priority. I'm guessing we're setting the miner thread to priority, maybe so that we don't take over the machine. At any rate, we create a new key, and we create this extra nonce and set it to 0. And while generate Bitcoins, we're going to sleep for 50. I don't know if that's nanoseconds or microseconds. I don't think might be seconds. I don't know. Is it a system call? It might be seconds. We'll check if we're shut down after sleeping. And while the V nodes are empty, we'll sleep for 1,000 time units, maybe seconds, and check if we're shut down again. So I guess, I don't know what the V nodes are, but maybe we have like no transactions or something to work on. So we're going to sleep for a longer time. And again, check if we're shut down after we wake up. And then we wake up and we get the transactions updated. I was reading N as number, but I think N is just a prefix that maybe tells you the type. And I think so far it's mainly been an unsigned int. So maybe it means something about unsigned. I don't know. But at any rate, we're going to have this transactions updated last. So these are the last updated transactions. And I don't know. I don't know what best means. We'll set the previous index to the to index best, and then we'll get next. We'll call it get next work required on the p index previous, which is an unsigned int of bits. Create a Coinbase transaction. So we'll create the Coinbase transaction that pays ourselves essentially. So we make a new transaction, we size it to 1. We set the previous out to null because previous out was where we proved that we had some money for the transaction. This is a Coinbase transaction, so there's no input, I guess. The previous out is null. Then for the script signature, we're going to write the bits and the extra nonce. So that's going to be the start. The bits is what? The previous index? I don't know if that's the idea of the previous block or what. But essentially, we're going to write the nonce, which right now is 0, and resize the output transaction to 1, and write our public key, because the public key is how you send money. And then we're going to write op check sig so that we tell the script to check the signature. Let me create a new block. And if we can't get the block after creating it, then we return false. I guess things have failed. And we add our Coinbase transaction as the first transaction of the block. Then we collect all the latest transactions into the block. We set the fees to 0 as a starting point. We call critical block on main and critical block map transactions. That's setting up some sort of critical section. We have this txdbr. I guess we're opening the transaction database as read-only, or at least for read. And we have this map test pool. I don't know what test means here. I don't think we're on the test network, but maybe we are. And we have this VF already added. We're calling VF already added on map transaction size. That's creating some vector. So these are, I guess, it's some list of all of the transactions that have already been added. That I guess those are all of the ones in map transactions. We said found something to true. We set block size to 0. And while we found something and block size is less than half the max size, then we said found something to false. We set n to 0. And we iterate over the map transactions. And if we've already added, okay, so now we look up, so the already added thing is like a map, right? It's really a vector, but we're going to, I guess, treat it, we're just going to index into it and see if we've already added the n, whatever n is, whatever we're indexing by n. And if we've already added it, we'll just continue. Otherwise, we have not added it, and we will look at mi, which is the whatever was in map transactions. The like map iterator, I guess is what it stands for. We'll look at the second, maybe that second in time, or maybe the second transaction. And if and that will give us a transaction. So I guess it's the second transaction. And if that transaction is a Coinbase or it's not final, then we're not going to add it to our blocks. We already have a Coinbase part of our block, and we want the transaction to be final, I guess, before we add it. And then we have this transaction fee requirements, mainly only needed for flood control. So to prevent people from sending us too many transactions. So under 10,000 or about 80 inputs is free for first 100 transactions. Base rate is 0.1 per kilobyte. So we get the min fee on the P block VTX size. This is a predicate. we're checking if the p block VTX size is less than 100. Where p block came from, I'm not sure. I don't think we saw it defined in this function. And that will give us the min fee. And then we call it map test pool temp on map test pool. Or no, we don't call it. This is creating a like a hash map. And if the transaction connect inputs, okay, so there's some connect inputs function on the transaction that you pass in the transaction database, the map test pool temp, the C disk position, I guess the place on your disk where the transaction lives, whatever 0 is, the fees, whatever false and true are in the minimum fee. And that's going to, I guess, try to connect inputs. And if we can't connect inputs, then we continue. Otherwise, I guess we've connected inputs, whatever that means, and we'll swap the test pool temp in the test pool. So this is the temp is like a candidate, I think, and the pool is like the real version. And if we are down here, then we the candidates have succeeded in some sense, so we make them real, I think is what's going on. And then on the P block, the VTX, I don't know what V is for, but some I guess vector of transactions. So we're going to push back. We're going to add the TX to the vector of transactions. And then we're going to increase the block size by the size of the transaction and whatever SARE network is. I guess like additional stuff for the network, maybe. And then we'll set already added to true to indicate that we've added the transaction. And we'll say that we found something. And we'll do that for all of the transactions. And I don't know what connect inputs is, but maybe we can peek into its implementation just to get a sense of what it's up to. Here. It must be defined in the CPP file. We have transaction to connect inputs. Doesn't really say. It says take over previous transactions spent pointers. Okay, so I guess this is the thing that says now that we have to make sure that the transaction is spending previous inputs. And I guess this is saying that we're marking somehow the previous inputs as spent so that we don't try to reuse them. That's what I'm going to guess is up there. And so that is why if this fails, then we can't add that transaction. Okay, so if we're down here, are we still in this function? Where are we? Oh, yeah, I scrolled over. I was confused there. Okay, so we have finished with this for loop here. So now we're down here. We're going to, I guess, whatever P block is. So this, I can just think of it as the block. So we set the bits to whatever bits is now. And we looked at the transaction vector and the vector of outputs and the value and set that to the result of calling P block get block value. And I think that maybe that's saying the transaction knows which block it's in, and we're setting the value of the block to whatever block we're building up, perhaps. And then we're going to log running Bitcoin miner with transactions, with some number of transactions in block, whatchamacallit. Passing in only the VTX size. Okay. And so that's built up some sort of block. And then we're going to, and this is just telling you how many transactions really you found for the candidate block. And then we have a pre-built hash buffer, some unnamed structs that have the previous block, hash, Merkle, root, time, bits, nonce, some padding, unsigned car, the hash and more padding, and I guess that's temp. And then we have this block version stuff. So this is the hash previous block is the same as the hash. So the temp block hash prev block is the same as the p block hash prev block. And they're both equal to the p index prev, or they're both equal to the result we get from checking if p index prev is true. If it's true, we call get hash block. Otherwise, we set it to 0. And similarly for the hash Merkle tree and so on and so forth. And then we call format hash blocks on the temp block and the temp hash one. And then we do the search. I'm guessing this is the non-search now. We get the time. We calculate the hash target by calling set compact, I guess, taking the p block bits, turning it into a big num, and calling uint 256 on it. That's the hash target. And then we also have a hash. And then in an infinite loop, we are going to create a SHA-256 block, 2 of them. One from the temp block, whatever n block 0 is in temp hash 1, and one from temp hash 1, n blocks 1 in hash. I don't really know how those differ or what they're up to, but maybe we'll find out. Okay, so hash target is going to be the thing with the number of zeros. And if hash is less than or equal to hash target, that comparison goes the opposite way that I thought it would. But I think if you have, well, somehow this is, I think, if we're in this loop, I'm guessing this is where somehow we check the number of zeros we have. And if we don't, I assume what this is saying is if we don't have the appropriate number of zeros, however that's modeled in this so far, then we set the p block nonce to the temp block nonce. This temp block is going to be like maybe like the candidate. Assert something that the hash is equal to the p block get hash. Debug print some stuff. Set thread priority to normal. And then we have this critical block thing. We'll save the key. I don't know what the key is at this point. And then we'll make a new key. Why? I don't know. Why are we saving the key and making a new key? And then we're going to process this block the same as if we had received it from another node. And to do that, we just call process block. This is, I assume the same process block is called by non-miners as well. And then we set the priority to the lowest again. We sleep for 500 and break. Oh, you know what? Maybe I was wrong. So I think this is saying that we do have enough zeros. And now we're like reifying the block as a real block. So that if we're down here, I guess we don't have enough zeros, but I'm not sure. So then we're going to update end time every few seconds. So ++ temp block nonce. We're going to AND with this OX3FFF. No, we're checking if something is 0, I guess. This may have like a modular flavor to it, I'm not sure. And then we're checking for shutdown. And if the nonce is 0, we break. If the previous index is not the index best, we break. If the transaction updated is not the transactions updated last, and we've, I guess, more than 60 seconds later, then we break. If we are not generating Bitcoins, then we break. Otherwise, we set temp block end time, the temp block end time set temp block and p block times to the maximum of median time passed and get adjusted time, and we return true. So I followed most of that, except I don't see where we try new nonces. But let's see what happens next. Yeah. So let's grab this. Let's go to main in here. Go to miner. What's it called? Bitcoin miner. Okay, so I think this is just Bitcoin miner. And then we could look at nonce. So we set the nonce to 1 here. Here we set the p block nonce to temp block nonce. I think this is if we have if we've met the target. And here we set the temp block nonce to 0. What is this doing? We're calling plus plus b. Okay, so we're incrementing extra nonce here. So I guess that's where we're starting. We're just starting at 0 and adding 1 every time. And so when do we get up here? So while generate bitcoins, we only, I guess, increment the nonce when generate bitcoins is called. So we try to create a block. Yeah. This just runs on an infinite loop. So I was looking maybe for like a loop that search for the nonce, but I think that we have this while forever loop, and we do a bunch of work. And if we get down at the bottom, the last thing we do is update end time. And if we have gotten down here and we haven't called process block, then our block essentially failed. And we go back up to the beginning with a new nonce. And the new nonce is 1 more than the previous nonce. And that's the original implementation of mining. Looks like. I was about to go, but then I saw something about stochastic approximation. I don't know what this is about. VF included, VF best, value size. This is what? Select coins. Okay, so I think select coins is about, you say you want to send like $100, and it's going to try to find which outputs to lump together to come up with that $100. And there's some algorithm for figuring out the best way to do that. Like maybe it's best to spend a transaction, maybe it's best to spend a lot of little transactions. Maybe it's best to spend the first sub $100 transaction and the next one. But you have to be careful, I guess, because you can, if you add big transactions first, I think you can get yourself maybe in a place where you don't have enough little transactions to make up the difference. So you have to figure that out. And then I think that what happens is you can find a transaction that gives you $300, and then you get change back as part of the Bitcoin script or something along those lines. So I'll stop there. What is that, about 2 hours and 24 minutes? Longer than a typical one, but I figured this code is relatively small enough, and people will want to see like all of the different parts of it. That's the original Satoshi Bitcoin code. That's all for me. Make sure to send some Bitcoin and or Monero to the addresses below. And see you again soon. Thanks for watching.